Hello, in this video let's discuss second question of today's contest. You are given a string S of consisting of uppercase English letters. You are allowed to insert at most one uppercase character at any position. Return the maximum number of LCT subsequences that can be found after adding at most one insertion. The constraints are n is up to 1 if I. So after adding any character at an index at most once, return the maximum count of LCT subsequences. If initial count is x, what can be the final answer? It will be surely greater than equal to x, because by adding new characters we can only increase the count of subsequence but we cannot decrease. So the answer will be simply the initial count of LC subsequence plus extra that we are getting because of extra character that we are adding. Firstly, how to find count of LCT subsequences without adding any character. So initially we have a string. So how can we find the number of subsequences of LCT in that without adding any extra character? So let's say we are at index C. If we are at character C, then what is the count of LCT subsequence that we get? It will be simply the count of L before into count of T after, because it should be LCT. So if we are thinking with respect to C, we can get a subsequence only if we have some else before and if we have some T's after. So what is the count? It will be simply count of L before into count of T after. For example, we have LLCT. Then what will be count? It will be simply 2, because we have this one LCT and this also LCT. So at every C we can get L before into T after, so that those are the number of subsequences with that C. In that way we can traverse the whole string and then we can find the answer. But for every index we cannot traverse from 0 to I minus 1 or I plus 1 to n to get the count, because at index I, if there is C, we have to traverse from 0 to I minus 1 to get the count of L and I plus 1 to n to get the count of T. We cannot do that always. So we can simply store two vectors, prefix count of L and suffix count of T, so that by traversing we can update in the vectors and also we can get the count in of 1. This is a possible method. Let's discuss other method also to find the count of subsequences. So let's say we have L. We can have any characters except LCT also, but they will not affect our answer. So simply we will consider only the cases when the character is L or C or T. So for now let's assume that we are at L. So firstly, if we want a subsequence of LCT, so there should be a subsequence of LC, or is there a possibility that there is no subsequence of LC and still we can get LCT? It is not possible, because for a subsequence of LCT to be existing, there must be subsequence LC also and there must be subsequence LT or CT also. So this gives us a way that, for example, we are dealing with a bigger wide range of LCT. So for now, we can just think of LC, so that at every T character, we can think of total LCT. So we have LCT. So let's first think of L. So without, for example, if in the given string there are no L's, can we get answer? Obviously no. So we should have minimum L's. We should have L so that we can get subsequence. So the first important thing is L. So okay, we have L. Then we do not have C. Then we can get the answer? No. Even then we cannot get the answer. So even if we have L, we should have LC also. Subsequence LC also. For example, we have CL, CLT. We have all LCT, but is there subsequence LCT? No. So to get final count of LCT, we must have LC also. So with L, we should have LC also. So we will keep some information with respect to L. And at every C, we can count the count of subsequences of LC. So now we got the subsequence count of LC also. Then we must have a T also. And before T also, we must have LC subsequence. Only then we can get subsequence. For example, we have TLC. Then can we get? Obviously no, because LCT should be in order. So at every T, then we can get the answer based on information we stored at LC. So instead of thinking at LCT, we can start thinking from every prefix, so that every prefix must be there to get the final answer. So at L, what is the information that we require? At L, we simply require that we have an extra L, so that at every extra C, at next extra C, we can get the answer. For example, we have LCT, and then we have L, and then we have CT. So for now, we computed till LCT and we are at L. So we are at L. So what is the count of L till now? It is 1. So after now it will be 2. So for the next C, what is the count of subsequence? It will be simply the number of L before plus T after. So for this C, what is the count of L subsequence? It will be 2, because we have 2 L's before. So at every L, if we increase the count of L, then at C we can get that these are the number of L's that we have till before, so that the count of LC will be incremented. So hope you got this. So for at every L, we simply want to increase the count of L so that it will be useful for every C. So for now we came at C. So at C, what are the things that we need to update? So at C we want C++ because obviously we reached C, and also LC plus is equal to L because we reached a new C. So at this new C, what are the count of subsequences LC that are ending at this C? It will be simply the count of L before. For example, we have 3 L's before. We have 3 L's before and this is C. So what is the count of subsequences, new subsequences that are ending at C? It will be simply 3 because we have 3 L's before. So the count of LC is 3. So at every C, increase the count of C and also increment the total count of LC subsequences by L because we reached a new C. So we got some new set of subsequences LC with the count of L. So simply LC plus is equal to L. And let's assume that we reached T. So at T, what are the things that we require? So we have reached T. So we have reached the final part. So at T, what is the thing that we want to get answer? It is simply the count of LC subsequences, right? So obviously we computed LC before. So if we are reaching a T, what will be the new answer? It will be old answer plus the new subsequences because of this T. And what is the count of subsequences because of this T? It will be simply the number of subsequences LC so far. So LCT plus is equal to LC. So in this way, by computing, I think there is no need of C++ also because we only want L, LC and LCT. So in this way, we can simply get the count of LCT without any adding extra character. But we should add extra character. So let's think of that now. So it is given that we can add any character at any index. So can we add A at any index or can we add Z at any index? Obviously no, because even if we add, we cannot get answer. So instead of thinking of all the ways, let's try to think what are the best ways to add and which characters. So from now, we can very easily understand that we will only add L or C or T anywhere because adding any extra characters will be of no use. So let's assume that we have 3 choices, like we have 3 possibilities, placing L or C or T at the beginning or end or in middle. So let's assume that we are thinking with respect to first and last only. So for now, let's assume that we are only adding at first index. So can we add L at beginning or C at beginning or T at beginning? We can add anything, but is there really use by adding C at the beginning? So let's say we have initial count of subsequences as 10, LCT count as 10, and now we are thinking with respect to 0th index. So we are at this, and is there any use by adding C here? Obviously no, right? Because these initial subsequences will always be same. And now, because of extra character we are adding, we have to get more subsequences, right? But we are adding C here. But there are no initial L's before this because we are adding it first index. We can have any T's here, but there is no at least one L in the before. So obviously, if we add C, the count of LC subsequences gain or extra here is 0. Because even if if we are adding C, there are no initial L's to get LC subsequences. So obviously, there is no need, no use to add C at the beginning. And can we add T in the beginning? It is the same case. Even if we add T in the beginning, how can the number of characters be increased? How can subsequence be increasing? Because these all subsequences are same as original. We are adding this character. So obviously there should be some LC before, so that only then our count will increase. But we are adding this at first index. So adding C or T at the beginning is waste. So at beginning we can add only L to get an optimal answer. So this is one observation. And similarly, can we add C to ending? Obviously no, because we are adding this, but we are adding this, right? So it will be useful only when we are adding T at the last, and only it will be useful only if we have LC. So simply, even at the last, we can only add TC. We cannot C, we cannot add C, or we cannot L, because even then, if we add those, they are useless. Because how can we get extra count by adding C at the end? So obviously we cannot. So simply, we can add L at the beginning, T at the end. But what about middle? So let's say we have. So let's say this is the character that we are adding at this index. So it can be L, or it can be C, or it can be T. And now let's think: is there any elimination possible here, like in the previous cases, or no? So let's say we are adding C here. For example, we are adding L here. Coming to L, let's start from L. So we are adding L in the middle. So we are adding L. what is the count of subsequences that will increase because of this L? It will be simply the count of subsequences of CT here, right? So we are adding L here. So when the count will be increasing, the count will be increasing only if we have CT subsequences in the right of L. So yes, this is useful, right? Because in this way, in this case, if we are adding C at the beginning, there is no increment in answer as well. But here we are able to get some count if there are CT subsequences. This is possible, right? There may be 100 cities here. So by this L, we can get 100 cities. But is this really useful? Let's think ahead. So we are adding this here L, right? So what if we, because we are assuming that we are already adding a L here in other separate case. So we are adding L here. And because of the first L, what is the count of subsequence that will increase? That also will be simply the count of subsequent CT. So, for example, the number of subsequences CT here are 10 after this index. So what can be the count of CT subsequence after this index? It will be surely greater than equal to 10, right? Because these 10 will already be included in this, plus CT subsequences in this also will be incremented in this, will be added in this. So there is no use of adding L here, right? Because even if we are adding L here, we are getting CT, but we already discussed that we are adding L in the initial, L at the 0th index. So then we will get more answer than this CT here. Hope you got this. Let's say we have 3 CT here and the total CT here are 10. So we are adding L here or we are adding L here. So is there any use of adding L here than here? Obviously no. Because if we add L here, we will get 10 subsequences. But if we add here L, we can only add at most 1. So if we add L here, we cannot add here. So if we add this, the answer can only increment by 3. So from this also we got that it is useless to add L or T in the middle. Even the same with T, because we are adding T at the end. So LC subsequence count here will surely be less than or equal to count here. So in this way we eliminated these two cases as well. So for now, what is the observation we got? We can add L at the beginning at optimal for optimal answer. We can add T at the end to get optimal answer, or we can add any index C middle to get optimal answer. If you have any doubt, comment below regarding this, or try to take more examples and think why adding L or T is useless in the middle. So how can we get answer now? So we got the observation, then how to find the answer? So if we are inserting C at index A, then what will be answer depending on? It will be simply the L's before C and T's after C, which we discussed originally. So how to find these? So let's say this is the original, these are the original character itself. And after computing this, let's decide what character we are adding. So for now, these LCT are original in the string itself. We are not adding it as like this, because these are the characters that we added. But for now, let's assume that these are in the given string itself. So now we are just traversing the string and thinking what to proceed, what to continue. So we reached L. So simply L plus plus, we reached C. So these both as in the same in the initial one. So for now, we are adding a extra C in the middle. So after adding extra C, we initially saw that it will be initial answer plus extra we can get. So after every index, we are trying to add C in the middle and think of what is the gain that we get, what is the extra answer that we are able to get. So at C, what is the gain that we get because of extra C that we add in the middle? It will be L's before into T's after. So how can we get these both? So as we are traversing, we are updating the count of L's, we are updating count of LC, we are updating count of LCT. So at an index I, after index I, we are adding C. So if we are adding C, then we can get count of L before I know of 1, because we are already adding L's as we are proceeding. So we got this L, and how to get T's after index I? So how can we add T's after index I? We cannot simply traverse of I to I plus 1 to n to get answer. So like as we are maintaining the count of LCT, we can count number of T's we found so far. So for example, if we find T, instead of only this, we can add T plus plus, because we can get the total counts before this, but we want t's after this. So simply initially maintain a total t variable and find a whole string and count the total number of t's in the string. So at an index I, till index I we are getting the count of t's also. So after this index we can get total count of t that we computed before minus the total count of t that we computed so far. So in this way at every index I we can get the count of L's before as we are computing it, and also we are able to get the count of t's after even in often by this way. So in this way we are able to get what is the extra part for every answer in off one. So in this way we got simply answer right. So we got this extra for every index. So we can simply maximize this by traversing the whole string. And then we can simply return answer. So extra is equal to L into total t minus t. T is the t count so far. Total t is the total count of t in the given string. And now we got the answer for adding c in the middle. But how to get when we are adding L in the beginning or t at the end? We can simply add L to the original string and then we can find the subsequences in this, or we can simply add t to the string and then we can find the answer. But even without this, can we do some changes in this only to get our answer without doing any extra often operations? If we think yes. So if we are adding L to the first, then what is the extra? It will be simply the count of CT subsequence, right? And similarly, if we are adding T, then what will be answer? It will be simply LC. The extra is LC because we are adding it. There will be no final or there will be no initial. So for T, the LC subsequence is answer is the extra part we can get, and at L the extra part we can get is CT. So in this way we can maintain two variables LC CT also, so that we can return finally the answer by considering these both cases as well. So we are maintaining C, we are maintaining L, we are maintaining C, we are maintaining LC, we are maintaining T also, because so that we can get the T's after this index in off one, and LCT obviously we want is the final answer, and then CT plus is equal to C. This is because we want the count of subsequences CT for the final condition when we are adding L. So in this way, by adding two other variables, we can simply get the answer in often. So let's check the code. We are simply initializing LCT to 0 and counting all t's, and then we are traveling the whole string, and if it is L we are incrementing, it is C then this, if T then this, and after doing all this, what is the extra part we are able to get? It is simply L into T minus the total count in T minus T so far. So in this way we can get extra part, and then we can so in this way we can just simply get extra part of everything, maximum extra part, and finally we can simply return maximum. LCT is the original subsequence and LC is the subsequence that we get when we are adding T at the last. CT is the subsequence that we get when we add L at the beginning, and extra is the part where if we add C in the middle. In this way we can get the answer. If you have any doubt, comment below. See you in the next video.